The International Society of Automation certification and certificate programs improve ROI, promote safety, improve productivity, and provide third-party endorsement of knowledge and experience. ISA currently offers 2 certification programs: Certified Automation Professional, CAP, and Certified Control Systems Technician, CCST. CAP certified professionals are responsible for the systems, software, and equipment used in control systems, manufacturing information systems, systems integration, and operational consulting. CCST certified professionals calibrate, document, troubleshoot, and repair instrumentation for systems that measure and control level, temperature, pressure, flow, and other process variables. Both certification programs require applicants to meet certain eligibility criteria and pass a multiple-choice exam. ISA offers review courses and study materials to help you prepare. Learn more at www.isa.org/certification. ISA also offers certificate programs, which require applicants to take a training course and pass an exam. The ISA 84 Safety Instrumented Systems Certificate Program includes 3 certificates based on the ISA 84.org/certificates. The International Society.
What is automation? Automation is the food you eat. Automation is the beverage you drink. Automation is the car you drive. Automation is the paper you read. Automation is scientific progress. Automation is the fuel in your car. Automation is the electricity in your home. Automation is what makes the world work. So how do you fit in? Automation is a career. Are you interested?
I became an automation professional because I like solving problems.
I became an automation professional because I wanted to help people through science.
Because I like to design and build things.
Because I'm fascinated to the practical applications of the theory.
To make the world a better place goes without saying, but I think that things we do as part of providing process solutions make industry work better, and it all goes hand in hand in making the world a better place, I think.
Automation professionals are people with a diverse set of skills. Who are you?
Engineer.
Management.
I am a United States Marine Corps veteran.
Digital marketing consultant.
Process automation manager.
I am a consulting engineer.
I'm a United States Navy veteran.
Instrumentation and controls engineer in training.
Their work spans multiple industries. Where do you see yourself? Automation is a $100 billion industry and is expected to grow significantly in the coming years. All around the globe, the automation industry is building a better world.
Hi, I'm Dr. Peggy Kuhn, and I am proud to be an automation professional. professional.
My name is Billy Walsh and I'm proud to be an automation professional.
Hi, my name is Jim Garrison.
Hey, I'm Rick Albrecht.
Hi, my name is Dr. Penny Chen.
Hi, my name is Sherry Harmeyer, and I'm proud to be an automation professional.
Bonjour, je m'appelle Antonio Alves et c'est avec fierté que je travaille dans le domaine de l'automatisation.
Hi, I'm Jeff Blue and I'm proud to be an automation professional.
Will you join us?
Good afternoon and hearty greetings to one and all who joined us, the GSET ISA Students Branch and ISA Gujarat section for the webinar on Industry 4.0. We welcome you all for the erudite session on the technological innovations. Today, we are bestowed with the presence of Dr. Chetan Bhatt, sir, currently the principal of Government MCA College, Maninagar, Ahmedabad. He started his career in LD Engineering College and became the head of department in the branch of Instrumentation and Control in the same college. He has achieved PhD in the field of Knowledge Engineering from Indian Institute of Science, Bangalore, and has a gold medal mastered in field of Electronic Design Technology from the Indian Institute of Science, Bangalore as well. He was also the head of department in LDCE College in the field of Instrumentation and Control and was also the head of department of VGEC Chandkheda in the same field. He was the principal of Government Engineering College, Gandhinagar, and is currently the principal of Government MCA College since July 2017. He has specialties in the field of Instrumentation and Control. He teaches more than 15 courses in UG as well as in PG engineering. Sir is currently a part of National Mission Project of Education funded by the Ministry of Human Resources, Government of India and executed by Indian Institute of Technology, Kharagpur. On top of that, he is also a lead for 5 projects which are food quality analyzers, telemedicine, ontology engineering, functional electrical stimulation, industrial data communication. He identified his specialties to be teaching, designing, instructional material and e-learning portal, educational institute and laboratory development, research and development in various interdisciplinary areas, electronic and electromechanical product design. He is awarded as Distinguished Instrumentation Professional Asia Pacific Region 14 by ISA in 2017. Also, he is awarded as Excellence in Education 2018 ISA USA. Now, I would request Dr. Chetan Bhatt sir to commence the session.
let me just have a brief what we have discussed. Say my presentation outline, it will be something like this. First, we have introductions of types of industry, then industry revolutions, and fundamentally terminology related to industry 4.0. Then we'll discuss about what is really industry 4.0, what are the standard development framework for industry 4.0. Then finally we'll discuss about automation technology trends, and as students or as academicians, what we should look out, what we have lookouts, how the automation technology is changing, that we'll discuss. So if we consider the types of industries, then we'll have a primary industries where we can say all the natural resources like mines or crude oil and gas, agriculture, field products, all it comes under the primary industries. The product of primary industries goes to secondary industries, where we'll have assembly or processing of that primary products. It will take place. We have a discrete processes as a secondary industries, and output of secondary industries, it goes to what we call the tertiary industries, where we have a testing, operation and maintenance, coding and tunings. All these activities we perform as a at tertiary industries. And we have a quaternary industries also, where basically we can say that it may not be directly in a path of supply chain, but we can say R&D activities or quality assurance, quality measurements, predictive maintenance, all this it comes under quaternary industry. We will discuss this with simple examples, like let us consider a extraction from oil field. It goes to say oil refineries, where final goes to some storage warehouse, and storage warehouse, then transportations of oil. We can say advertising, the selling point, or what we call a petrol pumps. All this it comes under a tertiary industry, or we can say the output. It is a tertiary production. Let us consider another simple. Here in agriculture fields, let us say we have a potatoes as a product. So it is a output of a primary industry. Then it goes to secondary industries, where that it is processed, and finally we have a potato chips. Then it is output of secondary industries. Now tertiary industry, or we can say tertiary services, are the outlets which sell the potato chips, where we have a customers and consumers, they buy it as a product. Now we can see that at every stage we have a added value. So value to products for a customer, it should be increased. So there is something called a concept of supply chain, and there is concept of value chain that we'll see. Now if we consider the segmentation of automations, then there are, we can say, roughly 4 categories of automation. One is a continuous flow process, like say oil refineries. The amount of productions, that is what we call a quantity, it is very large. But if we consider the varieties of product, it is simply it is a oil. So we can say that quantity is large, but we have a very minimal, or we can say single product. And the types of automations we used, it is what we call a fixed automation, where we and the type of process hardware, we can say it is a continuous flow process hardware. Second is what we call the mass manufacturing and discrete products. The quantity of productions compared to continuous flow process is reduced, but at the same time, the varieties of output products, it's comparatively larger. And the type of automation solutions we use, it is a programmable automation. Then next, it is a batch process. In batch process, we use a flexible automation systems. The varieties again it will increase compared to mass manufacturing and discrete products. And automation systems, it is very flexible to meet the requirement of the batch. Next segmentations, if we consider, that is jobs of production. It is the type of automation solutions we use. It is integrated automations. We can say that it is integrated in a machine tools itself, and the varieties of products we have from such types of systems, it is very large compared to all other types of processes. So if we consider the continuous flow process, oil refineries is one example of such processes. If we consider say mass manufacturing and discrete products, then appliances productions or automobile productions, it comes under this category. If we consider batch processes, then pharmaceutical industries and food processing industries, they have a batch processes, and all the CNC machines and all that machine tools manufacturing, it comes under the job productions. So here, if you look at the quantity, it is very large in one case, while variety is low. And another side, if you look at the variety of products we have, it is very large, but at the same time, the amount of quantity industry produce, it reduces. Now, if you look at the industry revolution, then now today we are talking about the industry 4.0. So this is what we call the fourth revolution of industry. Now, if we consider the historical development, the revolutions of industry, then first 1.0, we can say it is roughly started around 1784 in 1800 through the introductions of mechanical facilities with the help of water and steam power. So we can say that's the steam engine. It was first introduced, and it was used for industrial production. Now here if you look at there is no data is transmitted at remote locations and all. It is simply locally we have some measurements and we have some trivial testing at that. Now in case of industry 2.0, through the introductions of a division of labor and mass production, with the help of electrical energy, it was started around 1870, and hello. Yeah. Hello. So in Revolution 2.0, the applications of electrical energy, it was started. In first industry 1.0, it was only mechanical energy. In Revolution 3.0, the programmable logic controller and introductions of some microprocessor based systems, it was started in industry. Then first such applications, it was PLC from Modicon, that is Modicon 084. It was started in 1969. And we can say that till date we are now transition from industry 3.0 to industry 4.0. We have many applications what we can say as a industry 4.0 are becoming popular now in industry, and we are in the transition phase. And many technology which are used in industry 3.0 are contributing in industry 4.0 also. Now, if you look at this vertical axis, then amount of complexity, degree of complexity, it keeps on increasing. From if you move from industry 1.0 to industry 2.0, industry 2.0 to 3.0, and 3.0 to 4.0. And systems overall industries as a system or production plant, it becomes more and more complex. Now let us will discuss about some basic terminology which we can say which will be useful to discuss industry 4.0. Now when we say industry 4.0, then we are talking about digitalizations. We'll be talking about data, we'll be talking about informations, we'll be talking about AI and machine learning technology which directly deals with knowledge. And there is something called a generalizations, that is what in normal terms we call it a knowledge to wisdom, but in computer engineering or computer science point of view, we can say it is a generalization of purpose or generalizations of domain. Now, what is a data is, then any row signals or any row numbers, we call it is a data. Say suppose if I draw the sinusoidal signals without adding any context that what x-axis represents and what y-axis represents, then we can say it's simply data. So any signal variations without adding any context, we can say it is a data. To make it meaningful, what we need to do is we need to add a context to it. So some relations must be attached to data so that it becomes information. So suppose if I have a sinusoidal signal, and if I say that x-axis it represents the time and y-axis represents the voltage, then I can say that yes, it is a voltage variation with respect to time, and it becomes informations. Looking at the signals, we can say that how voltage vary with respect to time. Similarly, say I have some numbers, like say I'll say that 101 and 50 and 2, then it's simply a data, but it's some context to it, like say that 150 it is a gain, and 100 and 1 and 2 is a gain, then it becomes an information that yes, these are the data of bandwidth and gain of a electronic amplifier. Now you can see that in this graph, then if we move from data to informations, then it becomes more context independent and our level of understanding will increase. Similarly, now what is knowledge? Then when we process the informations, when we attach a purpose like reasons or principles or rationales and generate some know-how, or by processing the information, it becomes knowledge. So suppose I say that 150 is a bandwidth and 1 and 2 is a gain, then by processing that data, I can look at the pattern and I can see that 100 into 1 is 100 and 50 into 2 is 100. And then we can, by looking at the data patterns, we can say that gain and bandwidth products, it remains constant. So it becomes our knowledge. So to gain knowledge, we need to process informations. Now, what is the wisdom, or what we call the generalizations of purpose or competence in multiple domains? Multiple domain, then suppose let us we say if we have considered the analog amplifier, but if we consider our say vocal systems, then in vocal systems also, if we amplify the gain, our loudness will reduce. So the similar concept it's applied to vocal system also. So gain bandwidth products remains constant. So it means that there are many fundamental concepts which can be generalized and applicable to multiple domains. And if we able to generalize that, we can apply to multiple domain in multiple contexts. So this is what the terms will may be used in further discussion. Another term concepts we use, that is what we call the cyber physical system. So what is cyber physical systems? And we can say that a cyber physical system is a system in which a mechanism is controlled or monitored by computer-based algorithm. So we have a computer-based algorithms, and the system is monitored and controlled by that computer-based algorithm. So in cyber physical system, physical and software components are intervened. It is deeply intervened, able to operate on different spatial and temporal scales. So in space and time, they able to operate the different systems, and it exhibits multiple and distinct behavioral modalities and interact with each other in ways that change with context. So even if context change, then again they have a distinct behavioral modalities, and they add up to that change in context. So that is the property of characteristics of cyber physical systems, we can say. So such examples, if we consider of cyber physical system, then smart grid is one such examples. Autonomous automobile systems, it is again a examples of cyber physical systems. So say in smart grid, the load condition change, then again systems will similarly say in autonomous automobile systems, based on condition change, the autonomous vehicles will respond. So the cyber physical systems, it has the ability to sense the environment based on change in environment, context in environment. It will change its behavior and perform accordingly. Then another terms we use, that is what we call the IT, that is information technology and operational technology. So IT includes any use of computers. It may be even embedded systems, or it may be a server also. Different categories of hardwares, computers, storage, networking device, and other physical devices, or and infrastructures and processes that is used to create, process the digital data, store the digital data, secured and exchange all forms of electronics data. And when we say it creates or it receives the data, then we can say sensors part, it is also included in this. We have a sensors connected to either computers or embedded devices, and then it is transferred to other high-end computing devices where it is stored, it is processed, various reports are generated, various decision we have a decision making mechanisms, algorithms. So all this, it includes under the IT. Now, what is operational technology? Then here we are discussing about industry 4.0 for industry. So it is a operational technology, we can say it is traditionally associated with manufacturing and industrial environments. What it includes? So it includes industrial control systems such as supervisory controls and data acquisitions, building management systems, and many more. All control level hardwares, it comes under operational technology. Now another term that we use, that is what we called a value chain. So the idea of a value chain, initially it was pioneered by one American academician called Michael Porter. So in 1985, his book Competitive Advantage, Creating and Sustaining Superior Performance, he talks about the value chain, and he says that there are 5 steps or we can say value chain activities we perform with a product. So one is inbound logistics, that is the receiving, warehousing and inventory control. These are the activities we perform as a part of inbound logistics. Second is that is what we call the operations. So as a part of operations, we can say it is a value creating activities that transform inputs into products such as assembly and manufacturing. And then once the product is there available, manufactured, then we'll have a outbound logistics. So as part of outbound logistics, we can say activities required to get a finished product to a customer. This include warehousing, inventory management, order fulfillment, and shipping. Fourth step, that is what we call the marketing and sales. Here activities associated with getting a buyer to purchase a product, it is performed. And fifth activities, that is service, and service activities that maintain and enhance a product's value, such as customer supports and warranty services. So in case of supply chain, we have a products and supply to a various stages of industry. That is a supply chain. Here we don't talk about say value addition to, but in case of value chain, we are talking about value addition to the product. So that is a difference between supply chain and value chain. So in case of Industry 4.0, our objective is to use a digital technology to add a value in a value chain. Now industry. Now we discuss what's really Industry 4.0 is. So basically, Industry 4.0, we can say that it is a digitalizations at each and every hierarchy level of industry, and it goes beyond that. And reason is that nowadays internet is available everywhere and it is very simple and cheap. Everybody have internet access to the device, and devices are becoming intelligent. Maybe even if we consider our smartphone, it is having a internet access and it has many intelligence inbuilt, and we can have many other IoT devices which are very cheap, at the same time having a internet access and have some inbuilt intelligence, and they keep on collecting the data, and we can make use of such data meaningfully for various purposes. Using this in a smart way opens up a new world of services and functions. So using all this data, we can provide various different types of services and functions. It is possible nowadays. Industry 4.0 connects all parties involved in business process in the manufacturing and process industries. Starts from raw material supplier to customers end, and everybody we can connect with each other, and systems gets adapted according to the change in context or change in requirement, change in environments. Information from suppliers, customers, and within your own company is connected, and it is transparently available to all. Work pieces and machine manage the production autonomously. So machine and work pieces are used autonomously to produce things. So we can say it is a flexible, efficient, and we have a resource saving if we go for a digitalizations concepts of Industry 4.0. So there are the transition between sectors. Now companies and sectors, they are having a transitions. Now what is really Industry 4.0? Then what is available today? Then we have available cloud is available, network is available. We have a automation, devices with internet access, and internet-based services. If we consider the digital networks used in industry, it's having a long history. It starts from the 1990s. We have applications. We'll find application of digital network in industry, and gradually we have a various industrial communication protocols available. Say Modbus, Hard Protocol, Foundation, Field Bus, and all. And many of them, they have now even Ethernet abilities. Also, we have many industrial devices. So this is what we have available today. Now, what is new when we talk about, say, Industry 4.0, then we can say it is a uniform and sector neutral standards for services and semantics. हाँ. हाँ मैं करी चेंज. Hello. हाँ. So new, what is new addition to the current availability of Industry 3.0, say internet-based devices and all, then we can say it is a uniform and sector-neutral standards for services and semantics. So what do we mean by that? Uniform and sector-neutral standards. Then we have various industry sectors, and every industry sectors they use many similar devices. Then if we use the devices in one sectors, same devices in different sectors, then we should have a neutral standards with respect to sectors, and it should be uniform everywhere. And we should have a semantics attached to it. So if there is a functions, if there is a characteristics and descriptions of device, then we should have some intelligence inbuilt which can infer some meanings. So semantics means we can say it is some meaning out of the informations in a given context. It should be able to infer. System should be able to inform. That is what we called a semantics, and it should be neutral for sectors, and it should be uniform. And the move is from intranet to internet. So now it is not say only limited to enterprise, or we can say plant, but it goes to internet. Internet connectivity, it is available at all the hierarchy level. So that is what we call the industry. So if we add the current abilities plus uniform and sector neutral standards for services and semantics, and if we provide the internet abilities for all the devices, that is what we call the Industry 4.0. So that is exchanging information between value chain partners. So every partners in value chain, they have a relevant informations available to them. It is transparent, and for that we need to come up with a new business models and applications. Say suppose if we consider say discrete industries, then in case of say value chain stages, then one is product designs. Then once product, so product designs, that is what we call the product planning and prototype developments. Then production planning for manufacturing purpose. Then we have a production engineering stage, and then finally the productions. We have a product, and then final in value chain is servicing. So for product we provide a service supports. So for at each and every stage we use the digital technology. The relevant required informations, it is available stage, of value chain. So, suppose if we consider, say, some electronics card, then design of that product electronics card, that at product design stage we consider various aspects. We prepare a schematic diagrams, printed circuit boards and all, and then it goes to planning stage. So now at the planning stage we have available bill of materials and all, how we should plan our assembly line. That will be the production planning. So all the information, simulation results of product designs and all, it is available at production planning stage. Here it is even at production planning stage also we can have a simulations. We have a digital simulations which decides how we can optimize our production at the planning stage itself. Then production engineering, that is what we called, we deploy all the manufacturing hardware for particular production. And then finally we have that all the assembly line will start it and start producing a product. That is what in our case it's electronics card, and then it goes to market. Now when it is our electronics card with this customer also, we provide the service also. We collect the data of card digitally, we provide the digital assistance all. So at each and every stage we have some digital simulations, digital modeling, digital data, digital monitoring and controls. It takes place in discrete industry. The same case in process industries also. So we have a process. In the case of process industries, again the similar product designs it comes, then process and plant designs. Then once process and plant is designed, then we install and commissioning overall plant, and then our operation starts, and again product from the plant it goes to customer. So again in all these stages we'll use a various digital technology, and there are number of technology we'll use, and particularly when we say industry 4.0, then IT and all this operational technology, they are coming together. So if we look at the convergence of IT and operational technology, automation technology, then early 1970s it was started, and 2000s we can say that we have a well-defined 5-layer architectures of today's industry, where at the bottom we have a various input-output devices, where inputs devices we can say sensors, output devices all actuators or robotics arm. Then we have a programmable logic controller. On the top of that we have a SCADA systems. Then manufacturing education systems on the top of that, and finally enterprise resource planning. Here it shows only in this 5-layer architectures, it shows the confined to a one premises, one process industries or one enterprise we can say. It does not goes beyond that. But in future, or we can say industry 4.0, it goes beyond that. It integrates the overall plant with customer also. So that is the what we can say the concept of industry 4.0, where IT and OT now they are coming together, and every devices in industry they have a ability to communicate with each other. So I was talking about various technologies, digitalizations technology. So what are the drivers then for industry 4.0? Then one we can say autonomous robot. So autonomous robot, they can perform, they can sense the environment, they can adapt the environment, adjust their functions according to the change in environment, change in requirement, perform majority of the task without any manual intervention in a plant floor. And we nowadays we have a many use cases also of. Similarly, second is simulation. So simulations, all engineering students, they know what's real simulation is. We use simulation to represent the real world in a some and we run that model on how our system will behave. And there are many advantages of simulation. Say we can avoid the damage, we can have a safety of personnel, safety of instruments, because even if we make it error, it will not harm. And another big advantage of simulation is if system or product say system time constant, it is a very large, or the system is distributed over a space, so then it is many times it is very difficult to perform a real test. And where simulation will help, it will try, because time will just in a on a click of mouse will have a results available. Similarly, if system time constant is large, but it can be, we can say it can be compressed. Similarly, if system is distributed over a space, we can say that it can be compressed. Like examples I'll take, say oil distribution network, then oil from one location will transmit through pipeline to another locations, then it's a very large physically distributed environment systems. But if we have a good mathematical model available for such systems, we can easily simulate it. We can start the performance of various elements of the systems. If we change certain parameters of a devices, then how it will affect the system performance, that we can easily study. Third is horizontal and vertical system integrations. We have now communications and integrations, easy integrations available horizontally at the same level. Like all the IO devices, they can connect with each other very easily. They can communicate with each other at the same time. All IO devices, they can communicate with devices located at higher level in hierarchy. And it is very easy to integrate because of digital technology. And nowadays what we have a plug and play technology, and the technology called electronics device description and electronics device description language, and FDT. It aids this task. Another technology change development, that is industrial IoT or IoT. It also contributes to industry 4.0. Then when we say we are connecting all the devices, security, it is very essential, very important. Cyber security, it is again a technology which we need to consider when we talk about industry 4.0. And nowadays we have a good cyber security technology, and we can implement digitalizations at each and every stage with secured connections. Cloud, it is another technology, digital technology contributing to industry 4.0. In old industry 2.0, what we'll be collecting is process variables, simple primary variables we used to connect. Then in case of industry 3.0, when smart devices introduced into industry, they have their own ability to collect additional data other than primary variables. They can have some capability for predictions, fault tolerance, and all such abilities. It was introduced in devices. And now, not only that, say device related only the additional data, but we can have a health monitoring of various hardware of industries. It is possible, and all such huge amount of data we can transmit to cloud. We can store in cloud, and we can process those data, and we can come up with a meaningful information, meaningful knowledge for plant optimizations. Another technology, that is what we call the additive manufacturing. You all know is a 3D printing. So additive manufacturing, it can be used for even a prototype also. If we have a 3D models, we can easily develop a prototypes, or same hardware, printing hardware, it can be used to produce a multiple product. So additive manufacturing, it is again a changing the way industry is working. Then augmented reality, so we can have a virtual or total virtual representations of plant available at remote locations. Even we can feel some operator can feel he is like present in plant itself and observes various parameters of process hardware. Another technology, that is what we call the big data and analytics. So that cloud is connecting all the data, and we'll be using nowadays big data analytics tools to generate various insights, reports, and decisions. And last, that is what we call the AI and machine learning, artificial intelligence and machine learning. Nowadays, very powerful algorithms, even if we can implement on a simple embedded hardware, and we can implement some simple algorithms. Even machine learning algorithms can be implemented now in our mobile phone also. So there are many small size embedded devices are available in which we can implement AI and ML algorithms, and that AI and ML algorithms can be used for various purposes, and in field devices at customer side, customer support level, and many more it is possibilities. So we can say that industry 4.0, it is customer centric. It is more, we can say, stronger customer centric, because customer is in centers, and all value chain level, at all the levels we have a value addition for products, and customer will get benefited. Then if we consider for production processes, it becomes more efficient, and particularly for new marketing and business model, we need to come up with a new model of business and marketing. And this is all big contributions, because of we need to add a value in a production from one end to another end. And if we consider the transitions, then from 1987 to 2019, if we consider the value addition in value chain transformations, almost we can say it is 75% compared to 87. So if we consider to design a components or systems, industry 4.0 systems, what are the basic considerations we should have? What are the design principles? And one is that is what we call the interoperability. That is the ability of cyber physical system, humans and smart factories, to connect and communicate with each other via the Internet of Things, and what we call the Internet of Services. So it is connections of cyber physical systems, human and smart factories, and they should be easily connected, and they should be able to interact easily with each other. Then there is another called virtualizations, a virtual copy of smart factory, which is created by linking sensor data from monitoring the physical process with virtual plant models and simulation models. So we have a virtual plant models and simulation models available. All the data from factories we link with that model also, and really what is going on in plant, the same replications, virtual replications, it is available in our digital device. It may be a desktop, it may be a server, or it may be a tablet also. Then third is the decentralizations. That is the ability of cyber physical system within the smart factories to make decision on their own. So if something is changing, context is changing, environment is changing, condition is changing, or operational condition change is required based on customer needs, then they should be able to take their own decision and execute the manufacturing processes accordingly. So that is the decentralization of power at components level. Then another considerations, design principle, it is real-time capabilities. The capability to collect, analyze data and provide the insight immediately. So when we talk about, say, data available at remote locations or decision making through digital networks, then it should be immediately the decision must be taken and that actions must be taken. So real-time capabilities, it is very important in collections of data, analyzing the data and provide the immediate actions on it. Then fifth, that is the service orientations, offering the services that is of cyber physical systems, maybe humans or smart factories via the internet of services. So via internet of services, we should be able to provide a service effectively to customer. Then modularities, flexible adaptations of smart factories for changing requirements of individual modules. So at each and every modules level, if requirement is changed, then we should have a flexibility available, and my all the devices must be adaptable to that change. And for that, we should have a modular systems. We should develop, design, so that we can easily have incorporate the flexibility into it. So to achieve all this, what is required is now to go for Industry 4.0. Then one is common communication structure. That is, we have to have a common network and protocols, common rules for cyber security and data protections across the various sectors, across the various services, across the various devices. Then common languages including signs, alphabets, vocabularies, syntax, grammar, semantics, pragmatics, and culture. So we should have a common communication structure, common rules for securities, common language, so that every device, every system, it has a proper understanding without any communication gap. So everybody, they perceive same, they talk the same language. And when we say it should be common, then it means we should have a standards for that. So development of standards to achieve the objective of Industry 4.0, it is very important. So one such efforts which is going on, that is a reference architecture model Industry 4.0. We call it RAMI 4.0. Now, when we talk about that RAMI 4.0, then it has to consider what are the available current standards, and if certain requirements are fulfilled, then whatever the additional requirement, we need to add into it to develop a new standards. So that in case of RAMI 4.0, what they have considered is what are the available standards, then approaches for implementation of communication layer, particularly communication in industry. Communication layer, they have considered OPC UA, that is a basic IEC 62541 standards. OPC UA, that is if many students are aware about PLC and interconnect, then they are aware about OPC UA, that is object linking and embedding for process control, unified architectures. So if you have a different devices working with different communication protocol, then we use the OPC UA interface to so that they can interact with each other. So this OPC UA architectures, they have considered. Then approaches for implementations of an information layer. So at informations layer, that is the IEC Common Data Dictionary. So for data type they have considered the data dictionary of IEC standards, that is IEC 61360 series. Then characteristics and classifications and tools, that is again E-class, that is from European Union. They have used this standards. Hello. Yeah, this is next to that. So in case of this RAMI 4.0, what they have done is they have considered what are the available standards which can be used, and even with minor modifications we can adapt it. So for OPC UA, they have taken for communication layer, that stands for object linking and embedding for process control, and it is a unified architectures. Then for common data dictionary standards IEC 61360 they have used. Then for information layer characteristics, classifications, and for tools they have used the E-class from European Union. And nowadays in smart devices we'll be using electronics device description, and they have taken that EDD standards and field device tools, FDT, and DTM device technology tools management. So they have considered this standards for information layer. Then for functional and information layers, they have used the field device integrations as an integration technology. And for end-to-end engineering, there is something called a automation ML. So that is automation markup language. And basically, markup language is it is XML-based technology, XML using the XML technology, and which can be used to have a data objects or knowledge objects represented very easily using that well-defined markup language, that is automation markup language. Then process step, another, and again E-class for characteristics of integration level they have considered. So these are the available standards they have considered, and they have come up with a three-dimensional framework. So in three-dimensional framework, one dimension it represents life cycle and value stream, or we can say value chain. Another dimensions, that is hierarchy levels. That hierarchy levels, it is like what hierarchy levels we have in industry. Again, enterprise connected to one more higher level, that is the connected world. We'll discuss in details later. And third dimension, that is the layers. Now we'll see what the actually the part of all these levels. Then first dimensions, that is a product life cycle in value chain. Then first is a development, maintenance uses, then development and maintenance uses. So that construct a first part, it is a type and instance. So construction plan, that is a development, construction, or computer simulations and prototype developments are the activities we perform there. Then in model maintenance, we have a software updates, instruction manuals, and product changes. So all this it takes place at this model maintenance level. So here in this case of type, it is basically related to product development. Now in case of instance, the development stage, that is a part of productions. So producing the product, quality data related to it, and serial numbers related to product. Now, actually, these are the activities, but we have a detailed standards related to each and every activities. Say, if we can say product, then at instance level, how we define products. So product is an object. So in digitalizations, we use say concepts like object-oriented language. Like, so we have a class. So product is a class. Then what are the characteristics? How we represent it? How we exchange the informations related to product to other devices. So this all the standards requirements it is addressed this level. So when I say products or quality data, so it is just actions and standards related to every steps we execute perform at each stage we need to develop, or we there are standards available developed there. Similarly, when say maintenance uses at instance level, then there are services like maintenance service, optimization service, then updates, troubleshooting, recycling, everything it comes under the activities comes under this service stage, maintenance uses as an instance, and we should have to have a standards for that. Now, second dimensions, if we look at, then second dimension, that is a vertical business verticals, basic. So suppose if here if we look at these layers, asset, integration, communication, information, function, and business. So this comes at the second level, business ideas. So asset, integration, communication, information, function, and business. Now, if we look at assets, so let us we start with the business higher level. Then organization and business processes, it comes at this level. And the question is, what is the customer willing to pay for? So here, say collecting the data of users, we can say user survey and everything for product survey and everything, it is a part of this, and everything it is performed digitally. And then it goes to functional level. So what is my product supposed to do? My specifications of products and functions of the assets. Then accordingly, that information, what data does my product have to provide? So what the data it should be provided to hierarchy levels. So how do my customer access the data? So what type of data I should provide, and what type of access customers have access to informations, and integration of asset into world of information. Which part of my product are digitally available in the network, and how do I integrate my product with the process to move it in the real worlds. So things in the physical world, then integration of asset into the world of informations, the physical device, integration into digital world. So we can say that above this asset, all the data, everything it is a digital. Integration of asset into the world of information, access of information, how we communicate with the users, then necessary data, then functions as functional aspects of the assets, and then operation and business processes for customers. Now for the third layer, communication layer, they have considered communication technology available. They have in industry 3.0 nowadays, foundation, field bus, and industrial Ethernet and everything they have considered. And based on that, they have come up with this. So it is a OSI, same OSI architectures, physical layers. We have the data link layers, network transports. Now at physical layers, we have a wired and wireless devices. Then a data link layer, Ethernet, Wi-Fi, GSM or 4G. That is the data link layers it is used. Network layers, IP protocols, transport, UDP, TCP, and session, presentations, and applications layer, that is OPC UA, HTTP, and if it is IoT devices, MQTT. These are the protocols are adapted in communication layer. And this is actually, it forms the communication layer between product. So it is IO product, then field devices in industry, control devices in industry, then stations, various control stations, various workstations, enterprise, and connected to the world. So this is the communication in a hierarchy at different levels, and this is the architectures it is used. So here we can say that compared to say industry 3.0, this is our old architectures. Here we have a product and it goes up to enterprise. So industry 3.0, that is what we call our old world. Then it is hardware defines the structure. The structure of our plant and structure of our architectures, it is defined by hardware. Functions are linked to hardware. So many functions are linked to hardware, and flexibility compared to industry 4.0, it is a minimal flexibility, and communications with other devices, it is minimal. In case of industry 3.0, this field devices, they can communicate with control devices at supervisory or control levels. Control level, they can communicate with supervisory level as well as plant level. But this cannot be directly communicate with this level. So it means that communication is in hierarchy. So data flow from field level to enterprise level, selected data transmitted from one level to another. Similarly, selected data transmitted from enterprise to field device. So the product is isolated. There is a product is not connected with any plant side. So product is isolated. Now in case of industry 4.0, product is connected. So we have a various products. So this is a industry producing these products. Then in industry 3.0, products are not connected. But now in industry 4.0, products are connected with hardware of industry. We have a flexibility in factory. Any device can connect with any device if required. And beyond enterprise level, we have a connections with the world also. So through cloud and through internet services or some other communication networks. So in industry 4.0, the flexible systems and machines we have, functions are distributed through the networks. The network can cross company boundaries. So from company's boundary, they can cross and connect with the products or connect with the worlds also. Participant interact across the hierarchical levels. Across the hierarchical levels, communication is possible, and all participants are able to communicate with each other, and products are part of the network in case of industry 4.0. So if we consider this reference framework, then we have architectures, the real physical things and other digitalizations. Product, it also looks for life cycle, or we can say value chain part, and hierarchy also, communications in hierarchy also. So this RAMI 4.0, it's standards being developed for industry 4.0. So it is a three-dimensional map showing the most important aspects of industry 4.0, and it ensures all participants involved share a common perspective and develop a common understanding. And this is very important. Common perspective and developing a common understanding. And for that, many technology, and particularly when I was talking about knowledge, data, information, knowledge, and wisdom. So that basically wisdom, but we call it a generalization concept. And where artificial intelligence, knowledge engineering plays a very critical role in developing a standards so that various hardware components of industry, they can have a common perspectives and common understanding. So how Industry 4.0 will revolutionize the industry? Then we can say technology point of view, robotics will play very important role, replacing humans and assembly lines. 3D printing, manufacturing customized components, big data, that is again it plays very important role, collecting performance parameters, huge amount of data, big data and analytics, understanding the collected data. If we consider process point of view, then constant communication, data exchange between components, decentralization, decision making, routine decisions is taken in a decentralized manner. Then standardizations, ease of customizations, it is possible. Smart transport systems, automated transportations of raw materials, final products. It so we can say that products levels and outside world will be also integrated digitally. So if we consider people's point of view, then increased efficiency, so reduction in labor per units, and skill develop, upskilling, reskilling, continuous learning, and mindset change. It is required continuously upgrading the skills, reskilling, continuous learning. That is very important when we go for implementations of Industry 4.0. Only to handle disruptions. So monitoring and corrective actions, it is required. Routine actions, it will be performed automatically by robots. Now if we consider, we'll look at into just brief what's the trends and how we should look at. So industrial automation segment, if we consider, then future market segment by 2020, it is 153.3 billion US dollar market size it will be, which includes SCADA, PAC, RTU, DCS, safety devices, MES, MOM, all this, and all are highly digital devices having a many complex algorithms and capabilities incorporated into it. And industry segments which they use is MES and MOM technology segment is estimated to be the fastest growing market. DCS segment accounted for the largest share of the market by technology. Then APAC is expected to be the fastest growing market for industrial control and factory automations. Then simulators and PADO, that is also a growing segments. Industrial cyber security, if we consider the industrial control system security market, if we consider it is a 12.60 billion US dollar size in 2021, where IC 62443 standards, NERC cloud service, bring your own device, wireless technology, all this technology will be using. And for that, if people are bringing their own device and plant status is available, then security is very important. So all this internet, Modbus, Profibus technology, they are contributing, and that is the reason cyber security is another technology trend, and we need to look at that. So cyber attacks on critical infrastructure will drive the ICS security market. Database activity monitoring, IT solution to play a key role in the ICS and again it will play a critical role in security market. Then another technology and market, that is IoT and Internet of Device. So industry IoT market, that is by we can say it is 110.6 billion US dollar by 2025. It is a projections, but now even post COVID era, it may be even more than that. Then Internet of Things, that market with 2021 it is 1.6, and this is IoT first one. Then sensor, RFID, industrial robotics, 3D, all they will be using this IoT technology. Some condition monitoring in industrial IoT environments will have autonomous systems and guidance and steering, and all this technology will be you will be using IoT, and manufacturing sector held the largest share of this industrial IoT market. Real-time streaming analysis, security, data management, remote monitoring, again they will contribute huge to IoT markets. Cloud systems, it is projected as a US dollar 623.3 billion markets by 2025, where infrastructure as a service, platform as a service, database as a service, software as a service, software defined networks as a service, all this technology, it will contribute to cloud systems, and entire CRM or cross-functional role requirements, they will contribute to use of cloud systems. Big data analytics, again, this is old projections, but it almost crossed this $187 billion for big data analytics. Discrete manufacturing forecast, it is almost $22.8 billion. Banking predictions, it is 22.1. Process manufacturing, 16.4 billion. And technology as a part of this big data analytics will be using, that is big data as a services, Hadoop as a services. So in case of IoT, and when we connect a huge amount of data, there are certain structured data, there are certain unstructured data. So how we can make use of unstructured data in a meaningful way, then big data and Hadoop-like architectures, that will be useful. So analytics, visualizations of data as a service, and industry segmentation, smart machines, customer digital assistants, all this will make use of big data analytics technology, internet of automated composition engines and robots as a boss. So maybe at supervisory levels, we have a robot functioning, and we'll replace the human we minimize the human interventions. So all this technology then will use a big data analytics. So I will stop here. Will not discuss the use cases, and we'll take some question answer. हेलो हाँ चैट विंडो क्या પેલો છે हाँ 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 મને નથી દેખાઈ રહ્યા છે વિન્ડોમાં ઓકે ના દેખાય છે ફર્સ્ટ તો ગ્રીન સ્ક્રીનનો છે એટલે how functional safety and security is addressed in Industry 4.0. See, functional safety and security, it is a part of device as well as system integration part. So basically, Industry 4.0 look at device as an object. And whatever the requirement of functional safety and security, that will be embedded as a part of device. And still it is under process. So more information, it is not available. But basically, when we say it is a digitalizations, and all must have a common perceptions and understanding. The concept used, it is based on something like object-oriented components and knowledge components. So all the characteristics and part, it will be embedded as objects, considered as objects. And that will be integrated in a device or systems. Is there any ISA standard guiding for design and implementation of Industry 4.0 or training module to understand the hardware and software deployed for Industry 4.0? ISA, it is actively working with IEC and other organization in development of Industry 4.0 standards. Yes, there are many ISA standards are used being considered in development of Industry 4.0 standards. One is say intelligent device management standards. Then directly it can be with minor modifications, it can be used in Industry 4.0. So like say EDD or FDT, DTM, all these are ISA has actively worked in it. How can we be prepared for fourth industrial revolution? What environment impact will Industry 4.0 have for looking at current scenario? Industry 4.0, basically, the way we will work, it will change. So every functions, maybe that functions we perform in a plant or as a customer or as a service provider, everybody, the way they work, it will change. So they have to adapt with the change in requirement, the features and functionality added into systems by digital technology. That adaptability, it is very essential. And as in my slides from personal context, I have discussed that upskilling, that is the upgradations of skills, it is very important. Keep on learning, it is very important. And what environment impact will Industry 4.0 have as per looking at the current scenario? So environmental impact, we can look at environment impact in different context. Like if we consider the digital communications, then naturally communications change, speed of communications, quality of communication service, it is very important. At the same time, if we consider the impact on environment, then naturally that communication towers and all, it has its own environment impact. The technology, the product will use in Industry 4.0 or even in electronics products and everything, it has in environmental impact. But at the same time, we have a positive environment impact also, negative environmental impact also, because we can minimize or optimize the transportations, the raw material wastage, electrical uses, many things we can minimize. So it is very difficult at this time to, because it is environmental impact itself, it is a one subjects or we can say domain of research for industry 4.0, but and we can consider in many ways, if we consider the raw materials, then optimal uses of raw materials with high product quality and minimal energy uses. In that sense, it has a positive impact, but at the same time, communication, wireless communication, it has own impact. Fabricating or manufacturing devices, it has at the end of the life of product or system, it has its own impact, or even many devices, it has a impact on during the operation itself. So it is very difficult to discuss say impact. We need to consider many dimensions, but sure, the physical movements or physical it will be optimized. Any other question? Huh? Hello?
Yes, sir. The question is, can we change input parameters to change the production rate, for instance?
Production rate?
Yes, sir.
Yes, if we have a certain flexibility available in process hardware, yes. Same in many times in batch process also, we change that production rate. So flexible automations, when we say flexible automation, it means that we can have a flexibility in types of end product, as well as within a certain limits, we can change the production rate also.
So next question is, as Industry 4.0 deals with IoT/iOS, then all branches students share knowledge of it. Can you guide tools for learning that?
See, basically, when we say Industry 4.0, then it is an integration of information and communication technology in industry. So, students from, say, instrumentation control engineering background, or electrical engineering or electronics engineering, they must have some IT knowledge, basic IT knowledge. One cannot be a master of, say, AI and ML, or big data analytics, or cloud computing, but at least you can select one area and explore that for your core domain. Like suppose if we consider, say, smart grid, then electrical engineering students considering smart grid as a systems, how information and communication technology is contributing to smart grids, and what are the technology like, say, cloud computing, smart devices are implemented in a smart grid, that they should learn. But my first recommendations or suggestion is that basic IT skill is very important, and if students from information and communication technology, they have a IT background, but sometimes what I have observed is they are lacking in other dimensions. Like when we talk about sensors and actuators, all such devices, they don't have a knowledge. So if they explore those dimensions like sensors and actuators, it will be useful to IT and computer engineering students in implementing Industry 4.0. But AI/ML, cloud computing, particularly basic knowledge of database management systems, some cloud computing, AI/ML, it is essential for every engineer.
So next question is, as Industry 4.0 all about automation, then sir, what you think, how much time will it take to employ in India? And as well, the India is labor country, then I think it will affect the Indian people.
When we say it is automation, then naturally we are trying to make everything, all productions automatically. We are replacing certain labors there. But there is a reasons why we replace that. See, if we want a high quality products, consistent quality product, then we need to have a automations. So it will increase the other domains also, like say designing and development of IoT device, deploying of IoT device for various services. So all such roles it again creates employments. So naturally our people, or we can say laborers, they need to adapt the change and try to acquire certain skills to work in digital domain.
Yes sir, next question is, can quantum computing play a role in R&D section for simulations?
Quantum computing, basically it is right now we can say in a very preliminary stage, in a research stage. But if we have a well established, well matured abilities, hardware is available, then yes, in simulations it will play a very important role, because the amount of data it can process, the time it takes to process the data, it is very small. And it will help in simulations of very complex model, like say if we have weather forecast model, then it is a very complex model. So in a simulation of such complex systems, yes, it will help. Uh, supply chain, basically it is not a, we can say a value addition like system. It is a supply of products from one sector of one type of industry to another type of industry. So in case of industry 4.0, supply chain is a part of that, but we are talking about value additions by all these components of even supply chain also. So supply chain system, it will remain, but we have some additional uh, functions available, features available, useful for customers. Yes.
Okay, so now moving on towards it was a very interesting and knowledgeable webinar. Your remarks triggered new ideas that will benefit the youth for years to come. We hope everyone begins to implement your suggestions and confidently improve in this field. As we have approached to the end of this edited webinar, I would like to thank Mr. Chetan Bhatt for his valuable time and effort to make his webinar deeply insightful. I would like to thank ISA Gujarat Section Head, Engineer Jagdish Shukla Sir, and PN Parikh Sir, Senior Member of ISA Gujarat Section, for leading us in all possible ways and let us organize this webinar. We are also very thankful to CVM University as well as DH Patel College of Engineering and Technology for giving us a stage. Also, Team GSET ISS Students Branch is very thankful to Mr. Jatin Patel sir for the support and guidance and always stand beside us, being our shadow and keeping us away from any difficulty. We are also thankful to the student coordinator who are Anjali Shah and Harshil Mistry, and also thankful to the technical support given by Rushvit Mistry. Thank you to the design team of ISS Student Branch as well as publicity team for the support. And at last, thanks to the audience for their support and patience. We would like to gain a feedback from the fellow students who joined us today. Your feedback would be valuable for us to keep on arranging such insightful webinars in the future. Thank you.
Thank you.
Thank you, sir.
Thank you. Now I exit. I leave the. Okay. Bye.